everything that was in the first video of this chapter kind of gave you an introduction to what you'll need to understand to get to the ideas of quantum mechanics up through Einstein's work. In 1924, Louis de Broglie took this equation from Max Planck and started to rearrange it. This was actually part of his, actually it was his whole PhD thesis. Rearranged it and solved for wavelength, and then said, we know that E equals mc squared from Albert Einstein, and so he substitutes in mc squared for E. C cancels one of the c's in c squared, and we get wavelength equal h, which is a constant, over mc. Now that doesn't make sense for light, because even though light travels at the speed of light, it doesn't have a particular mass. But if we think of this not as just an issue of an equation for light, but an equation for a particle as well, then the wavelength of that particle, if we were to treat it as a wave, would be h, Planck's constant that we mentioned in the previous video, over the mass of the particle times the velocity of the particle. Mass times velocity, for those of you that haven't taken physics yet, is momentum. So any particle can be assigned or described as having a particular wavelength if we think of the particle as a wave instead of a particle. And its wavelength would be h over momentum, where h is Planck's constant. And we'll look at this from an example problem standpoint. What we're going to notice is that large objects that have a large mass, and or move very, very quickly, will have a wavelength that's so small you can't measure it. But small particles like electrons or atoms have wavelengths that are roughly their own size, or roughly the size of their measurable environments. And that means that for particles of that size, the ideas of quantum mechanics, the ideas of treating them as a wave instead of using Newton's force laws for particles, becomes a more accurate way, a more important way of predicting their behavior. It's interesting to note that this was de Broglie's PhD thesis. It's also why he got his Nobel Prize in 1929. And the reason why those things coincided is that when he turned in his thesis, his committee didn't understand it. So the people who were grading his work really didn't understand what was going on. So one of them got de Broglie to print an extra copy of the thesis and then sent it to Albert Einstein to ask him what he thought. And Albert Einstein wrote back, basically to paraphrase, and said, yes, this is very, very good work. Give that man his PhD. And then also immediately began lobbying and recommending for de Broglie to get a Nobel Prize for this work. And 5 years later, de Broglie was awarded a Nobel Prize. So this was very, very important, and it was counterintuitive to start to think of particles as waves. Planck and Einstein had showed that we could think of light, which was always thought of as waves, as particles. And de Broglie was showing the other way around, that if we use wave equations to describe the behavior of electrons instead of particle-type equations, we could get more accurate understanding of how electrons behave on atoms and molecules. Werner Heisenberg in 1927 worked out what started to become one of Einstein's, really a stick in Einstein's craw. Einstein, by the time quantum mechanics became a fully recognized theory, didn't like it. And part of the reason why is that this idea that we could not define a particular particle without measuring it, and that measurement had to do something to the particle. We couldn't measure as a casual, uninvolved observer. And the mathematics worked out to confirm this with quantum mechanics. It's not just a physical issue or experimental issue, but it's a mathematical and theoretical issue. That, for example, we can't know the position and the momentum of a particle explicitly both at the same time, because the measurements of those two things conflict with one another. to the point that the better we know the position, what we call x, of a particle, the worse we know its momentum, and vice versa. So this relationship, the delta, stands for difference, or really error or uncertainty. And so the uncertainty in the measurement of a position of a particle times the uncertainty in the measurement of a momentum of that particle has to be greater than h over 2 pi. H over 4 pi. Now h is a very, very small number, 6.626 times 10 to the minus 34. So this doesn't seem important until we get down to realizing the fact that the masses of electrons and the sizes of atoms are very, very small, so that the uncertainty in the position and momentum of a very small particle can be as large as its environment. And so Heisenberg's uncertainty principle can become important. And so again, to summarize, one can only know the position and the momentum of an electron or any other small particle with a certain degree of certainty, and that can become important, and we'll do some examples to talk about that. The big discovery in quantum mechanics, the one that really set everything in motion, was in 1926. Erwin Schrödinger was having some health problems. He went into the hospital to be treated for tuberculosis, was there for several weeks over a Christmas break, and when he came out, he had written several theoretical papers that postulated quantum mechanics, and they're all based around this equation that I've set up here. H psi, is the Greek letter psi, equals E psi. Psi is not just a variable, it is a whole function that we call a wave function, or some people will call it an orbital. It is a mathematical function that is set to describe a particular system that we're going to use quantum mechanics to describe. H is what we call the Hamiltonian operator. Again, it's not just a variable or a constant. It's a list of mathematical instructions that we apply in a certain order to this function. It can include derivatives and adding multiples and so on and so on. And then E is the energy of the particular particle, in our case as chemists, the electron, being described. So the idea here is that if we take this wave function and we apply certain mathematical operations of calculus and other things to it, by the time we finish applying all those operators, we finish applying all those mathematical instructions, what we have is the same function back multiplied by a particular number. And that number is the energy of the electron. And so what Schrödinger worked out that time while he was in the hospital was the form of the Hamiltonian, the exact instructions that needed to be done to generate energy for a particle, and then the actual wave functions for particles in several different kinds of systems. We're not going to go into the math involved in that in this class. Those of you that are chemistry majors will do that with me in your junior or your senior year. Those of you that are physics majors either will or have already done that, probably with Dr. Juronsky, in your quantum mechanics class in physics. What we're going to do as chemists is skip over the calculus, skip over the wave mechanics and the mathematics involved, and look at the results of that math, because as much as some of that mathematics can feel complicated to someone who hasn't had a couple semesters of calculus, it's not terribly difficult math, but it's Calc 2, Calc 3 type math. The results of it are fairly easy to understand. A lot of whole numbers work out. And so we're going to talk about that over the rest of this chapter and really of this course. As it turns out, whenever and this is something that Schrödinger was able to prove, when we have a wave function that appropriately describes a system, the square of that wave function will give us the information that we need to find that particle in a particular region of space. So what works out of this is that when we calculate the energy for a particular electron, it's always related to some whole number that we'll call the principal quantum number, and the letter we assign to that is lowercase n, and that's a number that's going to be 1, 2, 3, or some larger whole number, and that depends on the size of the energy level, on which energy level we're on in that particular atom. And then the second quantum number that comes out is L, lowercase l, and that's the angular momentum quantum number. That's going to define the shape of the area where we're most likely to find a particular electron. So that when L is 0, we have a spherical shape or spherical orbital. When L is 1, we have a dumbbell or double teardrop shaped orbital that you probably called p orbitals in high school. And when L is 2, the shape gets more complex as L gets larger. And on any particular energy level, L can be any number, any whole number between 0 and n. So on energy level 1, L can only be 0. You only have the s orbital, the spherical shape. On energy level 2, L can be 0 and it can be 1. So you have spherically shaped orbitals and you have dumbbell shaped orbitals. And we'll get into the pictures of the shapes of the orbitals in a little bit more detail in a little while. Additionally, for orbital shapes that can have direction to them, how they're arranged, what direction they're arranged in, is going to be determined by a third quantum number that we call m sub L, or the magnetic quantum number. And that's a number that can be for any particular L. For example, if we're on level 1 and we're at, if we're on level 2 and we have L equals 0 and L equals 1, spherical orbital can only be set up in one direction because it's a sphere. Just moving it, changing its direction doesn't change it at all. But a dumbbell-shaped orbital, a p orbital, an L equals 1 orbital, is oblong, so you can set it up on an x-axis, a y-axis, and a z-axis. And that corresponds to m sub L being -1, 0, and 1. So the number of different directions a particular orbital can be set up in is related to the shape in this way. Whatever L is, m sub L can be anywhere between -L and +L. And so this particular table, and you can pause the video and look at this in a little bit more detail, gives us, for any particular energy level, 1, 2, 3, 4, 5, and so on, the possible m sub L's that exist. On level 1, since L has to be less than n, you only have one m sub L. That corresponds to one s orbital. And each orbital can hold 2 electrons. We'll talk about why in the next video. On level 2, L can be 0 or 1. That corresponds to s and p orbitals on level 2. And when L is 1, we have 3 different directions, 3 orbitals. Now notice how this goes up. When L is 2, we're dealing with d orbitals. We have 5 possibilities from -2 to +2. And so the d sublevel, since 2 electrons can fit in each orbital, holds 10 electrons. And you can see how it builds up from there. And so we're going to get into, in the next video, talking about how to build an atom, how to know what orbitals the electrons exist in based on this mathematics. And so that's where we're going to pick up next time.